and welcome. Tonight, we'll explore 100 facts about wormholes. Settle in as we journey through the theoretical passages that may connect distant corners of the universe. Let your mind drift as we discover what science tells us about these extraordinary structures. Let's begin. A wormhole is a hypothetical structure connecting two separate points in space-time. Think of it as a tunnel with two openings, each potentially located in different places, different times, or both. The concept emerges from the mathematics of Albert Einstein's general theory of relativity, written in equations that describe how matter and energy warp the fabric of space and time. Though wormholes have never been observed, the mathematics allows for their existence, presenting a tantalizing possibility that has captured imaginations for decades. The term wormhole was coined by physicist John Archibald Wheeler in 1957. Before that, these structures were known by more technical names. Wheeler chose the term to help students visualize the concept, comparing it to a worm boring through an apple. Instead of crawling around the surface from one side to the other, the worm creates a shortcut straight through the middle. This simple analogy has helped generations understand how wormholes might work, offering a path through space-time rather than across it. Wormholes were first mathematically described in 1916 by Ludwig Flamm. Just months after Karl Schwarzschild published his solution to Einstein's field equations, Flamm realized another solution was possible. While reviewing Schwarzschild's work on black holes, Flamm discovered that the mathematics also described what he called a white hole, a theoretical time reversal of a black hole. These two entities could be connected by a bridge through space-time, forming what would later be recognized as the first mathematical description of a wormhole. Albert Einstein and Nathan Rosen rediscovered and expanded this idea in 1935. Working at the Institute for Advanced Study in Princeton, they published a paper titled "The Particle Problem in the General Theory of Relativity." They weren't trying to create a device for space travel. Instead, they sought to describe elementary particles without encountering mathematical singularities, those troublesome points where equations break down and values become infinite. What emerged from their work was a mathematical description of bridges connecting two regions of space-time. These bridges came to be called Einstein-Rosen bridges, and they represent the foundation of modern wormhole physics. The Einstein-Rosen bridge was not originally conceived as traversable. Einstein and Rosen's solution described a structure that would exist for only an instant before collapsing. In 1962, physicists John Archibald Wheeler and Robert Fuller demonstrated that these wormholes would pinch closed faster than light could pass through them. Even a photon entering one end would find the passage collapsing before it could emerge from the other side. The mathematics was beautiful, but the reality was frustrating. These bridges through space-time seemed forever out of reach. Wormholes are based on solutions to Einstein's field equations. These elegant mathematical expressions describe how mass and energy curve the geometry of space-time. The equations tell matter how to move, and they tell space-time how to curve in response to that matter. Solutions to these equations reveal possible configurations of space-time, including the warped geometries that could form wormholes. The mathematics doesn't guarantee that such structures exist in nature, only that they're consistent with our understanding of gravity. The Schwarzschild wormhole exists only in theory as a non-traversable structure. Named after Karl Schwarzschild, this solution describes the space-time geometry around a non-rotating, spherically symmetric mass. At its heart lies a singularity, a point of infinite density where the equations break down. The Schwarzschild solution includes a bridge connecting two regions of space-time, but this bridge exists only mathematically. Any attempt to pass through would fail as the structure collapses before anything could traverse it. It remains a theoretical curiosity, a glimpse of what the equations allow but nature may forbid. In 1988, physicist Kip Thorne and his graduate student Michael Morris changed everything. A few years earlier, Thorne had received a phone call from his friend Carl Sagan, who was writing the novel Contact, and needed a scientifically plausible way for his protagonist to travel to the star Vega, 26 light-years away. This conversation sparked Thorne and Morris to work on the problem, and their paper, Wormholes in Space-Time and Their Use for Interstellar Travel, a tool for teaching general relativity, introduced the concept of traversable wormholes. These weren't the collapsing Einstein-Rosen bridges. These were stable structures that could, in principle, allow matter to pass through safely. The Morris-Thorne wormhole requires exotic matter to remain open. This is perhaps the most challenging requirement. Exotic matter is not simply rare or unusual. It's matter that possesses negative energy density, something that seems to violate our everyday understanding of physics. In our normal experience, energy is always positive. The vacuum of empty space is considered to have zero energy. But exotic matter would have less than zero, creating a kind of negative pressure that pushes outward rather than pulling inward. This strange property would be essential for preventing the wormhole from collapsing under its own gravity. Exotic matter must violate the null energy condition. In general relativity, energy conditions are rules that describe how matter and energy should behave. The null energy condition states that the energy density measured by any observer moving at the speed of light should be non-negative. Exotic matter breaks this rule. Its energy density, measured by these light-speed observers, would be negative. This violation is not a flaw in the theory, but a necessary feature for traversable wormholes. Without it, gravity would crush the wormhole throat closed before anything could pass through. The Casimir effect provides a real-world example of negative energy. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed very close together in a vacuum would experience an attractive force. This happens because the vacuum between the plates suppresses certain quantum fluctuations, creating a region with slightly less energy than the surrounding space. In 1997, physicist Steve Lamoureux measured this effect experimentally, confirming Casimir's prediction. The Casimir effect demonstrates that negative energy densities can exist in nature, at least on tiny scales. However, The Casimir effect produces far too little negative energy for macroscopic wormholes. The effect works only at distances smaller than a few micrometers, and the amount of negative energy is minuscule. To stabilize a wormhole large enough for a person to pass through, you would need enormous quantities of exotic matter, far beyond what the Casimir effect could provide. Some calculations suggest you would need more exotic matter than exists in the entire visible universe. This remains one of the greatest obstacles to creating traversable wormholes. A wormhole throat is the narrowest part of the tunnel. This is the region where the two openings connect, the bottleneck through which everything must pass. The size of the throat determines whether the wormhole is traversable. If the throat is too small, tidal forces, the difference in gravitational pull between your head and feet, would tear apart anything trying to pass through. For human traversal, the throat would need to be at least several meters across, and the exotic matter must be distributed properly to keep it from collapsing. The shape function describes how a wormhole's geometry varies with distance. Mathematically, this function determines how far you must travel through the wormhole to reach the other side. In the Morris-Thorne solution, the shape function has specific properties. It must satisfy certain conditions at the throat, where it reaches a minimum value. Moving away from the throat in either direction, the shape function must increase, eventually connecting to two asymptotically flat regions of space-time. These mathematical requirements ensure that the wormhole has the right structure to be traversable. The redshift function determines the gravitational effects near the wormhole. It describes how time flows at different points along the wormhole's length and affects how light is redshifted or blue-shifted as it travels through. To avoid an event horizon, that point of no return found in black holes, the redshift function must be finite everywhere. If it were to diverge, it would create a region from which nothing could escape. The Morris-Thorne solution carefully avoids this problem by choosing a redshift function that remains well-behaved throughout the wormhole. Wormholes could theoretically connect two different locations in our universe. Imagine stepping through a door in one galaxy and emerging instantly in another galaxy, billions of light years away. The space between those 2 points, though, would still exist, but you wouldn't have to traverse it. Instead, you would take a shortcut through a different dimension of space-time. The wormhole would fold space in such a way that those distant locations become adjacent through the throat. This property makes wormholes fascinating for potential interstellar travel. Wormholes might also connect two different universes entirely. Some solutions to Einstein's equations allow for multiple disconnected regions of space-time, each potentially forming its own universe. A wormhole could, in principle, bridge these separate universes, creating a passage from one realm of existence to another. This possibility stretches even further into speculation, as we have no evidence that other universes exist, let alone that wormholes could connect them. Yet the mathematics permits such structures, inviting us to imagine realities beyond our own. Primordial wormholes might have formed in the early universe, though this remains entirely theoretical. In the first fraction of a second after the Big Bang, the universe underwent rapid expansion, and intense quantum fluctuations. During this chaotic period, some theorists have suggested that microscopic wormholes could have formed naturally. If they existed, these primordial structures would have been incredibly small, perhaps around 10 to the negative 33 centimeters, the Planck length. The universe's subsequent expansion could have stretched and distorted them, though most would likely have collapsed almost immediately. No evidence for such structures has been found. Matt Visser proposed that cosmic strings with negative mass could potentially sustain wormholes. Cosmic strings are hypothetical one-dimensional defects in space-time that may have formed during phase transitions in the early universe. If such strings existed and somehow possessed negative mass, they could theoretically provide the exotic matter needed to hold wormholes open. Visser suggested in 1995 that if these exotic cosmic strings were generated in sufficient numbers during the universe's birth, there might be many wormholes scattered throughout the cosmos. This remains highly speculative on multiple levels. Cosmic strings themselves have never been detected, and ones with negative mass are even more theoretical. The stability of wormholes is a major theoretical challenge. Even if exotic matter exists in sufficient quantities, keeping a wormhole stable presents problems. Small perturbations, such as light passing through or quantum fluctuations, could destabilize the structure. Some analyses suggest that wormholes would be prone to runaway instabilities, where tiny disturbances grow exponentially until the wormhole either collapses or explodes. Studying these stability issues requires understanding not just general relativity, but also quantum effects in curved space-time, a realm where our current theories become murky. Quantum effects might destroy wormholes before they become useful. According to semi-classical gravity, which attempts to incorporate quantum mechanics into general relativity, vacuum fluctuations would build up near a wormhole's throat. As virtual particles constantly appear and disappear in the quantum vacuum, their energy would accumulate in the wormhole's geometry. Some calculations suggest this accumulation would cause the energy density to spike to infinite values, destroying the wormhole instantly. This phenomenon is related to Stephen Hawking's chronology protection conjecture. Stephen Hawking proposed the chronology protection conjecture to explain why time travel might be impossible. In 1992, Hawking suggested that the laws of physics conspire to prevent the formation of closed time-like curves, paths through space-time that loop back on themselves and allow travel to the past. He playfully invoked a chronology protection agency as a metaphor for whatever mechanism enforces this rule. The idea is that when conditions approach those necessary for time travel, quantum effects automatically intervene to prevent it. If true, this would also prevent the creation of time machine wormholes. Wormholes could theoretically be converted into time machines. If you take the two mouths of a wormhole and move one at high speed while keeping the other stationary, time dilation effects from special relativity would cause the moving mouth to age more slowly. Eventually, a time difference would develop between the two ends. Step through the stationary mouth and you emerge from the moving mouth at an earlier time relative to where you started. This creates a pathway to the past, but only back to the moment when the time difference was first established. You couldn't use it to visit times before the wormhole became a time machine. Morris, Thorne, and Yurtsever published their time travel work in 1988. Their paper, Wormholes, Time Machines, and the Weak Energy Condition, explored the possibility of converting a traversable wormhole into a device for backward time travel. They showed that by manipulating the two mouths of a wormhole, either through motion or by placing one near a massive object, you could create a time difference between the ends. The implications were stunning and troubling. Such a device would allow for travel to the past, raising all the paradoxes that science fiction has explored for decades. The grandfather paradox is the most famous time travel paradox. Imagine traveling back in time and preventing your grandparents from meeting. If they never met, your parents would never be born, and neither would you. But if you were never born, how did you travel back in time to prevent their meeting in the first place? This logical loop seems impossible to resolve. The paradox demonstrates the severe conceptual problems that arise when backward time travel is possible. It challenges our understanding of causality, the principle that causes must precede effects. The Novikov self-consistency principle offers one resolution to time paradoxes. Russian physicist Igor Novikov proposed that any actions taken by a time traveler must be self-consistent. In other words, you simply cannot prevent your grandparents from meeting because that event already happened in a way that led to your existence. Any attempt you make would fail or would turn out to have been part of the causal chain that led to your birth all along. This principle suggests that the timeline is rigid, that history cannot be changed even by time travelers. It preserves causality, but at the cost of denying free will to time travelers. Many worlds' interpretations provide another possible resolution. In this view, traveling to the past would cause the timeline to branch into multiple parallel universes. When you go back and prevent your grandparents from meeting, you create an alternate timeline where you were never born. But your original timeline continues to exist, unchanged. You can never return to your original timeline because you're now in a different branch of reality. This interpretation preserves free will and avoids paradoxes, but requires accepting the existence of countless parallel universes. No experimental evidence for wormholes has ever been found. Despite decades of astronomical observations using increasingly powerful telescopes, no one has detected any sign of wormholes in nature. Astronomers have looked for gravitational lensing signatures, distinctive patterns in how light bends around massive objects. They've searched for unusual energy emissions and peculiar motions of stars. But every observation has come back negative or has been explained by more conventional phenomena. If wormholes exist, they are either extremely rare, extremely small, or both. Observational surveys have placed upper limits on wormhole abundance. Studies using data from large astronomical surveys have calculated how many wormholes could exist in the observable universe without having been detected. These limits are stringent. If stellar mass wormholes were common, their gravitational effects would have shown up in surveys of stars and galaxies. The fact that we see no such effects means that if macroscopic wormholes exist at all, they must be extraordinarily rare, perhaps only a handful in the entire observable universe. Some scientists have suggested that supermassive objects at galaxy centers might be wormholes instead of black holes. At the heart of most galaxies, including our Milky Way, lies a compact object millions or billions of times more massive than the Sun. These are generally believed to be black holes, but some researchers have pointed out that certain wormhole solutions could produce similar observational signatures. The challenge is distinguishing between the two. Recent observations of supermassive black hole shadows and gravitational waves are helping to test these ideas. And so far, all evidence points to black holes, not wormholes. Gravitational lensing could potentially reveal the presence of wormholes. When light from a distant source passes near a massive object, the object's gravity bends the light's path, creating multiple images or distortions of the source. This phenomenon has been used to study black holes, galaxies, and dark matter. Wormholes would also bend light, but in subtly different ways than black holes. By carefully analyzing the patterns of lensing, astronomers hope they might someday distinguish wormhole signatures from those of black holes. So far, no such signature has been found. In 2022, physicists simulated wormhole dynamics using a quantum computer. A team led by Maria Spiropoulou at Caltech and Daniel Jafferis at Harvard performed an experiment using Google's Sycamore quantum processor. They created a simplified model that exhibited behavior consistent with a traversable wormhole in curved spacetime. By manipulating quantum bits, they sent information from one part of the system to another in a way that mimicked quantum teleportation through a wormhole. This wasn't a real wormhole in physical space, but a quantum system whose behavior, according to certain theoretical frameworks, might be mathematically equivalent to one. The experiment provided insights into potential connections between quantum entanglement and space-time geometry. The experiment tested predictions from the holographic principle. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space. It's a profound idea, linking quantum mechanics with gravity. The quantum wormhole experiment explored a specific realization of this principle called the ADS-CFT correspondence, which relates gravity in a higher dimensional space to quantum physics on its lower dimensional boundary. The results appeared consistent with these theoretical connections, though their interpretation remains a subject of ongoing scientific discussion. The quantum simulation required suppressing errors in the quantum computer. Quantum computers are extremely sensitive to noise and errors. The wormhole simulation demanded high-fidelity operations because the signal they were looking for was delicate. If error rates had been even 50% higher, the signature would have been completely obscured by noise. The Sycamore processor's low error rates were essential to the experiment's success. This highlights both the achievement and the challenge. Observing these quantum gravity effects requires exquisite control over quantum systems, something we're only beginning to develop. Some physicists questioned whether the experiment truly represented a wormhole. After the results were published in Nature, other researchers pointed out that the model used in the simulation was quite simplified. Norman Yao and colleagues from Harvard published a comment arguing that the model was too simple to capture the essential features of gravitational systems like wormholes. The debate continues about how to interpret the experiment. Does it genuinely probe the physics of wormholes, or is it merely an interesting quantum information experiment? The answer depends partly on how literally we take the mathematical connections between different physical systems. Wormholes appear frequently in science fiction. From Star Trek's stable Bajoran wormhole connecting the Alpha and Gamma quadrants to Stargate's network of artificially created portals, science fiction has embraced wormholes as plot devices for decades. They offer writers a way to move characters across vast interstellar distances without violating relativity's prohibition on faster-than-light travel. While taking dramatic license with the science, these stories have helped popularize the concept and inspired real physicists to think more deeply about whether such structures could exist. Carl Sagan's Contact featured one of the first scientifically informed depictions of wormholes. When Sagan was writing his novel in the mid-1980s, he wanted a realistic mechanism for interstellar travel. He reached out to Kip Thorne, who was then developing his ideas about traversable wormholes. Thorne's input helped Sagan craft a scientifically plausible narrative where humanity uses an alien-built wormhole network to travel to distant star systems. The novel and subsequent film brought the concept of traversable wormholes to mainstream audiences while grounding it in real physics. The movie Interstellar presented one of the most accurate visual representations of a wormhole. Released in 2014 and directed by Christopher Nolan, with Kip Thorne serving as executive producer and scientific consultant, the film depicted a spherical wormhole near Saturn. The visual effects team at Double Negative worked closely with Thorne to create images showing how a wormhole would actually appear, accounting for gravitational lensing effects. The result was a stunning visualization where both sides of the wormhole were visible at once, with light from the far side bending around the sphere to reach the observer. This attention to scientific accuracy set a new standard for science fiction. The interstellar wormhole was placed by advanced beings to save humanity. In the film's narrative, a mysterious intelligence has positioned the wormhole to give humans access to potentially habitable worlds around a distant black hole. This concept aligns with the scientific understanding that naturally occurring traversable wormholes are unlikely. If such structures exist and are stable, they probably require advanced engineering by a civilization with capabilities far beyond ours. The film explores the idea that the wormhole might have been created by future humans, creating an interesting causal loop. Wormholes might exist at the Planck scale, though this is highly speculative. The Planck length, approximately 10 to the negative 35 meters, represents the smallest meaningful length in physics. At this scale, quantum fluctuations become so intense that our classical understanding of space-time breaks down. Some theories suggest that space-time itself might have a foamy structure at this scale, with tiny wormholes constantly appearing and disappearing. If such quantum wormholes exist, they would be far too small to traverse and would exist for only the briefest instance, but they could play a role in the fundamental structure of space-time. Without a complete theory of quantum gravity, this remains conjecture. Loop quantum gravity might naturally incorporate microscopic wormholes. This approach to quantum gravity attempts to describe space-time as being made of discrete loops and nodes at the smallest scales. Some researchers working in this framework have found solutions that include wormhole-like structures emerging naturally from the quantum geometry. These wouldn't be macroscopic, traversable wormholes, but tiny quantum features of space-time itself. Understanding these structures might help us develop a complete theory of quantum gravity. String theory solutions include wormhole-like structures. In string theory, fundamental particles are replaced by tiny vibrating strings, and space-time itself emerges from the interactions of these strings. Certain string theory solutions include wormhole geometries, and some versions of the theory suggest that wormholes might be created through stringy effects. The Randall-Sundrum models, which invoke extra dimensions beyond the familiar 3 of space and 1 of time, propose scenarios where wormholes might exist without requiring exotic matter, at least in certain configurations. However, string theory itself remains unproven, and these wormhole solutions are mathematical possibilities rather than confirmed physical structures. The ER equals EPR conjecture links wormholes to quantum entanglement. Proposed by physicists Juan Maldacena and Leonard Susskind in 2013, this idea suggests that Einstein-Rosen bridges, the wormholes from the 1935 paper, and Einstein-Podolsky-Rosen entanglement, the spooky action at a distance from quantum mechanics, are actually the same phenomenon viewed from different perspectives. When two particles are entangled, their quantum states are connected regardless of distance. Maldacena and Susskind propose that this connection is actually a tiny wormhole in space-time geometry. This remains a conjecture, but it has profound implications for understanding the relationship between quantum mechanics and gravity. If ER equals EPAR is correct, entanglement could be understood as creating tiny wormholes. Every pair of entangled particles in the universe would be connected by a microscopic wormhole. These wouldn't be traversable in the conventional sense. You couldn't send matter through them. But from this perspective, quantum information might be understood as being shared across them. This viewpoint could help explain why entanglement seems to violate our intuitions about locality, why measuring one particle can instantly affect another far away. The wormhole interpretation provides a geometric way of thinking about this quantum connection, though it's important to note this doesn't allow faster-than-light communication. Traversable wormholes would require enormous amounts of energy. Even if exotic matter exists, stabilizing a wormhole large enough for human passage would require energy levels that dwarf anything we can produce. Some estimates suggest you would need the equivalent of the mass energy of Jupiter, or even a significant fraction of a galaxy. This isn't just a technological hurdle for today's civilization. It represents a fundamental challenge that might be insurmountable for any civilization, no matter how advanced. The energy requirements alone might make macroscopic traversable wormholes forever impractical. Creating a wormhole might require manipulating the fabric of space-time directly. This would involve technologies far beyond our current capabilities, machines that could warp and shape space-time geometry at will. We don't even know if such manipulation is physically possible. It might require matter with properties we've never observed or control over quantum fields in ways we haven't imagined. Some physicists have explored what such technologies might look like in principle, but the gap between principle and practice appears vast. Microscopic wormholes might be easier to create and stabilize, though this remains theoretical. Recent theoretical work suggests that very small wormholes, perhaps just large enough to transmit information, might require far less exotic matter than macroscopic ones. Some researchers have explored wormholes sustained by electrically charged fermionic matter, particles with half-integer spin like electrons. These solutions would still be extremely challenging to realize, but calculations suggest they might not require the galaxy mass quantities of exotic matter that larger wormholes would need. If such micro-wormholes could somehow be created, they couldn't transport humans, but there's speculation they might allow for faster-than-light communication, though many technical and theoretical hurdles would remain. A wormhole network could connect multiple locations across space and time. If one traversable wormhole is possible, then in principle, many could exist simultaneously, creating a transportation network spanning the galaxy or even the universe. This is a common theme in science fiction, from Stargate's network of ancient portals to more recent stories. However, maintaining such a network would face all the stability problems of individual wormholes multiplied many times over. The interactions between nearby wormholes could create additional instabilities or enable paradoxes if the network allows paths that loop back in time. Roman rings describe configurations of multiple wormholes arranged in a circuit. Physicist Tom Roman and his colleagues studied what happens when you connect 3 or more wormholes in a closed loop. Even if none of the individual wormholes is a time machine on its own, the combination could create closed time-like curves, allowing travel to the past. Matt Visser analyzed these configurations and found them particularly problematic. They seem to amplify the chronology protection issues, suggesting that if one wormhole time machine is impossible due to quantum effects, a network of them would be even more so. Wormholes might have distinct observational signatures in gravitational waves, if they exist. When black holes or neutron stars merge, they emit gravitational waves ripples in space-time detected by observatories like LIGO and Virgo. Theoretical calculations suggest that if wormholes existed and collided or merged, they could produce gravitational wave signals different from those of black holes. The differences would be subtle, related to how the exotic matter affects the space-time curvature, but potentially measurable with sufficiently sensitive instruments. As gravitational wave astronomy advances, scientists might be able to set increasingly stringent limits on such signatures, or, if we're extraordinarily fortunate, detect signals consistent with wormholes. The event horizon of a black hole differs fundamentally from a wormhole's throat. An event horizon is a one-way membrane in space-time. Once you cross it, you can never return, because doing so would require traveling faster than light. The throat of a wormhole, by contrast, allows two-way travel. You can pass through in either direction. This difference is crucial. It's what makes wormholes potentially useful for travel, while black holes remain ultimate dead ends. The presence or absence of an event horizon determines whether a compact object is a black hole or possibly a wormhole. Rotating black holes have more complex structure than non-rotating ones. The mathematics describing spinning black holes, the Kerr metric, includes an inner horizon and a ring singularity rather than a point singularity. Some early speculations suggested that you might pass through a rotating black hole and emerge somewhere else, making it a kind of wormhole. However, detailed analysis showed that such traversal would be impossible. The interior of a Kerr black hole contains regions where causality becomes so twisted that they're effectively impassable. Any realistic journey would end at the singularity, not at another part of the universe. White holes are hypothetical, time-reversed black holes, though they're considered even less likely to exist than wormholes. If a black hole is a region of space-time from which nothing can escape, a white hole would be a region into which nothing can enter. Matter and light could only flow out of a white hole, never in. The Einstein-Rosen bridge, in its original form, connected a black hole to a white hole, with the bridge being the wormhole. White holes are extremely speculative. There's no evidence they exist, and most physicists believe they probably don't. If they did exist, they would seem to violate the second law of thermodynamics by spontaneously ejecting matter and energy, creating entropy, decreasing processes that don't occur in nature. Wormholes would likely have strong tidal forces near their throats. Tidal forces arise from differences in gravitational pull across an object's extent. Near massive compact objects, these forces become extreme. Your feet might experience significantly stronger gravity than your head, stretching you in a phenomenon gruesomely called spaghettification. The Morris Thorne wormhole was specifically designed to minimize tidal forces at the throat, making it safe for travelers. But many wormhole solutions would have tidal forces strong enough to tear apart anything trying to pass through. Engineering a truly human-safe wormhole would require careful design. The amount of exotic matter required might be reduced in modified theories of gravity, though these theories remain speculative. General relativity isn't necessarily the final word on gravity. Various modified theories have been proposed, including F-R, gravity, where the equations depend on functions of the Ricci curvature scalar, and other variations. Some of these theories allow for traversable wormholes without exotic matter, or with much less of it. In these frameworks, the structures would be held open by the modified gravitational dynamics rather than by exotic matter. However, these modified theories must still match all observations of gravity in the solar system and beyond, a stringent constraint that limits which modifications are viable. None have been confirmed to describe reality better than general relativity. Asymptotically safe gravity is one framework that might permit more realistic wormholes. This approach suggests that gravity becomes well-behaved at very high energies due to quantum corrections that emerge naturally. Some researchers have found wormhole solutions in asymptotically safe gravity that require less exotic matter than the standard general relativity solutions. These wormholes might be more feasible, though we're still far from being able to create or observe them. The approach remains speculative, as we don't yet have a complete theory of quantum gravity to test against observations. The geometry of space-time around a wormhole would create unusual visual effects. Light would bend in strange ways as it passed near or through a wormhole. Distant stars would appear displaced, stretched, or duplicated. If you looked into a wormhole, you would see the region around its far mouth, with that view nested inside the view of the near region in complex ways. The visual effects team for Interstellar computed these effects accurately, showing how light from the distant end would wrap around the sphere. The result is beautiful and disorienting, a reminder that wormholes would distort not just space, but also our perception of it. Wormholes might play a role in quantum computing beyond just simulation experiments. The entanglement structure of quantum computers shares mathematical similarities with wormhole geometry. Some researchers have proposed that understanding these connections might help design better quantum algorithms or more stable quantum computers. The idea is that by thinking about quantum information as flowing through geometric structures analogous to wormholes, we might gain new insights into how to manipulate and protect quantum states. This remains highly speculative, but represents an interesting intersection of quantum information theory and gravitational physics. The weak energy condition is the least restrictive of several energy conditions in general relativity. It states that the energy density measured by any observer should be non-negative. The null energy condition, which exotic matter violates, is a special case applying to observers moving at the speed of light. There are also stronger conditions like the dominant energy condition, which requires that energy cannot flow faster than light, and the strong energy condition, which relates to whether gravity is always attractive. Wormholes violate the null energy condition, and many solutions also violate the weak energy condition. These violations mark exotic matter as genuinely exotic. Quantum field theory allows for temporary violations of energy conditions, while classical physics insists that energy densities must be positive. Quantum mechanics is more flexible. Virtual particles constantly appear and disappear in the vacuum, and in certain circumstances, these quantum fluctuations can create brief periods of negative energy density. The Casimir effect is one example. These violations are always small and short-lived, limited by quantum uncertainty relations. Nevertheless, they demonstrate that nature permits negative energy densities in principle. The challenge is scaling these effects up to macroscopic sizes and durations. Squeezed vacuum states are another quantum phenomenon involving negative energy. In quantum optics, you can manipulate the quantum state of light to reduce uncertainty in one property, at the expense of increased uncertainty in another. These squeezed states can have regions of negative energy density. Researchers have created squeezed states in laboratories and used them to improve the sensitivity of gravitational wave detectors like LIGO. While these states contain negative energy, they also contain positive energy nearby, and the total energy remains positive. The negative energy is localized and transient, far from what's needed for wormholes. The average null energy condition attempts to limit how much energy conditions can be violated. Even though quantum effects allow temporary violations of the null energy condition, there might be limits on how long and how much the violations can persist. The average null energy condition says that when you integrate the energy density along a null curve, a path followed by light, the total must be non-negative. This would prevent sustained macroscopic violations. If this condition holds, it would severely constrain or perhaps entirely rule out traversable wormholes. However, physicists have found some scenarios where even this averaged condition might be violated. The cosmological constant might affect wormhole solutions. The cosmological constant represents a uniform energy density pervading all of space, what we often call dark energy. Its presence causes the universe's expansion to accelerate. When you include a cosmological constant in Einstein's equations and solve for wormhole geometries, the solutions change. Researchers have studied Morris-Thorne wormholes in de Sitter and anti-de Sitter spacetimes, which have positive and negative cosmological constants respectively. The dark energy can affect the stability and required exotic matter of these solutions, sometimes making them slightly more favorable. Wormholes might exist in higher dimensional spacetimes. String theory and some other approaches to fundamental physics suggest that our universe might have more than the three spatial dimensions we perceive. The extra dimensions could be curled up at very small scales or could be large but hidden from us in other ways. In these higher dimensional spaces, wormholes might be easier to create or stabilize. Some brain world scenarios where our universe is a three-dimensional surface in a higher dimensional space, allow for wormhole solutions that avoid some of the problems of the standard four-dimensional case. The membrane paradigm provides an alternative way to think about black holes and wormholes. In this approach, you don't think about what's inside the event horizon, but focus on its surface, treating it as a membrane with physical properties like electrical conductivity and viscosity. This perspective can sometimes make calculations easier and provides intuitive pictures of how black holes interact with their environments. Some researchers have extended membrane paradigm thinking to wormholes, considering the throat as a kind of membrane. This hasn't solved the fundamental problems, but it offers different insights into wormhole physics. Phantom energy is a hypothetical form of dark energy that might exist in our universe. It would have even stranger properties than ordinary dark energy, with an equation of state where pressure is less than negative, 1 times energy density. If phantom energy exists, it might be able to support traversable wormholes without requiring exotic matter in the conventional sense. However, phantom energy creates its own problems. It would cause the universe to end in a big rip, where accelerating expansion eventually tears apart all structures. Most physicists consider phantom energy unlikely to exist, making this potential solution to the wormhole problem questionable. Quantum gravity effects might change wormhole physics fundamentally at very small scales. All the classical calculations assume that general relativity holds even at the Planck scale, but we know this can't be true. Quantum fluctuations become dominant at such tiny distances. A complete theory of quantum gravity, whether it's string theory, loop quantum gravity, or something else, would predict how wormholes behave at these scales. It might prevent their formation, stabilize them in unexpected ways, or reveal entirely new types of wormhole structures. Until we have such a theory and can test it, we're working partially in the dark. Information passing through a wormhole would not violate causality if the wormhole doesn't allow time travel. As long as both mouths of the wormhole exist at the same moment in some reference frame, and there's no time difference between them, sending information through is no different than sending it through normal space, just faster. The wormhole acts as a shortcut, but cause still precedes effect. It's only when you manipulate the wormhole to create a time difference between the mouths that causality issues arise. Then signals could arrive before they were sent, creating the possibility of paradoxes. The ethics of creating wormholes raises profound questions. If we ever develop the technology to make traversable wormholes, who would control them? Could they be weaponized? What would happen if a wormhole mouth were placed near a massive object, allowing it to swallow enormous amounts of matter? Could wormholes be used for surveillance, creating portals to spy on distant locations? And if wormholes enable time travel, what ethical frameworks would govern their use? These questions are premature given our current understanding, but they're worth considering as we explore the theoretical possibilities. The relationship between wormholes and black hole. Information loss remains unclear. Black holes present a famous paradox. Information that falls in seems to be lost forever, violating quantum mechanics' principle that information must be preserved. Stephen Hawking spent decades working on this problem. Some physicists have speculated that wormholes might play a role in resolving it. The idea is that if wormholes somehow connect the interiors of black holes to other regions, perhaps information isn't truly lost, but emerges elsewhere. The ER equals EPR conjecture is partly motivated by trying to understand this issue. However, we still don't have a complete solution to the black hole information paradox, and the role wormholes might play, if any, remains a matter of ongoing research. Traversability requires more than just having a throat that doesn't collapse. The wormhole must also be short enough to traverse in reasonable time. If the tunnel through the wormhole stretched for light years, it wouldn't provide much advantage over conventional travel. The Morris-Thorne solution allows for arbitrarily short wormholes, but this requires specific configurations of exotic matter. Additionally, the trip through the wormhole should be smooth, without encountering singularities or regions of extreme space-time curvature that would destroy anything passing through. Meeting all these requirements simultaneously is exceptionally difficult. The future of wormhole research lies at the intersection of many fields. Progress will require advances in quantum field theory, general relativity, observational astronomy, and potentially experimental physics if we ever develop ways to create exotic matter. Understanding wormholes might also require breakthroughs in quantum gravity, string theory, or other fundamental physics. The challenge is daunting, but the potential rewards are equally profound. Whether or not traversable wormholes can exist, studying them pushes the boundaries of our understanding and forces us to confront the deep structure of space-time itself. Some wormhole solutions involve non-spherical geometries. While the Morris-Thorne wormhole has spherical symmetry, mathematical solutions exist for wormholes with different shapes. Flat-faced wormholes, sometimes called stargates in the literature, would have planar rather than spherical mouths. The mathematics becomes more complex for these asymmetric configurations, and they typically require even more exotic matter than spherical wormholes. These alternative geometries remain purely theoretical, interesting mathematical exercises that show the flexibility of general relativity's equations. The throat radius must satisfy specific mathematical constraints. For a wormhole to be traversable, its shape function must meet certain requirements at the throat. The radius there must be a minimum, and the geometry must flare outward on both sides. This flare-out condition is essential, ensuring that the wormhole doesn't simply end in a dead end, but connects to two distinct regions. Violating these geometric constraints would create something other than a wormhole, perhaps a black hole or some other exotic structure. The mathematics is unforgiving in what it permits. Wormholes could theoretically form bridges between different moments in time. Beyond connecting distant locations, wormholes might link different eras. If you could create a time difference between the two mouths, perhaps by accelerating one to near light speed while keeping the other stationary, the wormhole would connect not just places but times. Step through one mouth and you might emerge from the other years or centuries before you entered. This property makes wormholes potential time machines, raising all the paradoxes and problems that come with backward time travel. The energy requirements scale with the wormhole's size. A microscopic wormhole might require relatively modest amounts of exotic matter, perhaps equivalent to the mass of a small asteroid. But as you scale up to human traversable sizes, the energy requirements grow dramatically. A wormhole with a throat radius of 1 meter might require exotic matter equivalent to Jupiter's mass. Scale up to a throat wide enough for a spacecraft, and you might need mass energy equivalent to a significant fraction of the Milky Way. These scaling relationships make macroscopic wormholes seem increasingly implausible. Some researchers have explored wormholes in higher dimensional theories. If our universe has more than 3 spatial dimensions, as some string theory models suggest, wormholes might behave differently in those extra dimensions. In certain scenarios, the extra dimensions could help stabilize wormholes or reduce their exotic matter requirements. However, these ideas rely on frameworks that themselves remain unproven. We have no direct evidence for extra dimensions, and testing these theories presents enormous challenges. The higher dimensional wormholes remain mathematical constructions, awaiting experimental validation of the underlying physics. The redshift function determines how time flows along the wormhole. This mathematical function describes how clocks would tick at different points as you traverse the structure. If not chosen carefully, the redshift function could create an event horizon, making parts of the wormhole unreachable. The Morris-Thorne solution uses a constant or slowly varying redshift function to avoid this problem, ensuring that travelers can move freely through the entire structure. Different choices of this function lead to wormholes with different properties, some more exotic than others. Asymptotically flat wormholes connect to normal space-time at their ends. The term asymptotically flat means that as you move far from the wormhole's throats, space-time gradually approaches the flat, empty geometry described by special relativity. This is a desirable property because it means the wormhole could exist in an otherwise normal universe. Not all wormhole solutions are asymptotically flat. Some connect regions with different cosmological constants or curvature properties. Understanding how wormholes interface with their surrounding space-time is crucial for determining whether they could exist in our universe. The Ellis wormhole is a specific solution that's particularly well studied. Discovered independently by Homer Ellis and K.A. Bronikoff in 1973, this wormhole solution has no event horizons and is fully traversable in both directions. It's sustained by a scalar field with unusual properties rather than conventional matter. The Ellis wormhole, also called the Ellis drain hole, serves as a useful teaching tool because its mathematics is relatively simple, while still capturing the essential features of traversable wormholes. Many modern analyses start with the Ellis solution before exploring more complex geometries. Wormhole mouths could theoretically be moved and positioned. If you could create a wormhole, you might also be able to move its openings to different locations. This would allow you to place one mouth near Earth and the other near a distant star, creating a permanent transportation link. However, moving the mouths would require enormous energies, potentially as much as creating the wormhole in the first place. The mouths would respond to forces and accelerations like any massive object, though their internal connection would remain intact during the journey. This movability makes wormholes potentially useful as permanent infrastructure for a spacefaring civilization. The stability analysis of wormholes involves complex perturbation theory. To determine if a wormhole would remain stable, physicists analyze how it responds to small disturbances. Does a tiny ripple in the exotic matter distribution die away, or does it grow exponentially, tearing the wormhole apart? These stability calculations require advanced mathematics, solving differential equations that describe how perturbations evolve in the curved space-time geometry. Most analyses find that wormholes are unstable to at least some types of perturbations, though a few special configurations might be stable under certain conditions. The quantum field theory of curved space-time is essential for understanding wormhole stability. When you combine quantum mechanics with the curved space-time of general relativity, new phenomena emerge. Vacuum fluctuations, the constant creation and annihilation of virtual particles, behave differently in curved space than in flat space. Near a wormhole's throat, these fluctuations could accumulate, potentially causing the structure to collapse. Calculating these quantum effects requires sophisticated techniques from quantum field theory, and the results often suggest that quantum mechanics conspires to prevent traversable wormholes from existing. Some wormhole solutions involve electric or magnetic charge. Just as black holes can carry electric charge, wormholes might as well. Charged wormholes have different properties than uncharged ones, with the electromagnetic fields contributing to the space-time curvature. In some scenarios, the electromagnetic energy itself might provide part of the negative energy needed to stabilize the wormhole, potentially reducing the amount of exotic matter required. However, highly charged objects tend to attract opposite charges from their environment, quickly neutralizing themselves, so charged wormholes might not remain charged for long. The Morris-Thorne solution allows for arbitrarily low tidal forces. By carefully choosing the shape and redshift functions, you can design a wormhole where the tidal forces at the throat are as small as you like. This is essential for human traversal, as strong tidal forces would be lethal. However, reducing tidal forces typically requires steeper gradients in the exotic matter distribution, which might make the wormhole harder to create or less stable. There's always a trade-off between making the wormhole safe and making it feasible. Wormholes and quantum entanglement might be fundamentally connected. The ER equals EPR conjecture suggests this deep relationship, but the connection goes beyond that specific proposal. Quantum mechanics allows for non-local correlations between distant particles, while general relativity describes the geometry of space-time. Wormholes represent a geometric connection through space, while entanglement represents a quantum connection between systems. Understanding how these two types of connection relate to each other could be key to developing a theory of quantum gravity. The mathematics hints at profound links we're only beginning to understand. Some physicists have proposed that quantum foam might contain wormhole structures. At the Planck scale, quantum fluctuations might be so violent that space-time itself fluctuates wildly, forming a foam of tiny, constantly changing wormholes and other exotic geometries. This quantum foam would be invisible at larger scales, smoothing out to the continuous space-time we observe. If this picture is correct, wormholes wouldn't be rare exotic structures, but fundamental features of space-time at its smallest scales. However, without a complete theory of quantum gravity, this remains speculation. The thin shell formalism provides a way to construct certain wormhole solutions. In this approach, you imagine cutting two regions out of space-time and gluing them together along their boundaries. The boundary becomes a thin shell of matter whose properties determine whether the resulting structure is a wormhole. This formalism makes some calculations easier and allows for construction of wormholes with specific properties. Matt Visser used thin shell methods to design his cube-shaped and other exotic wormhole geometries, demonstrating the flexibility of general relativity. Dynamic wormholes that change size over time have been studied. Most analyses focus on static wormholes that don't change, but time-dependent solutions exist as well. A dynamic wormhole might expand, contract, or oscillate. These time-varying structures face additional stability challenges beyond those of static wormholes. The changing geometry would generate gravitational waves and might trigger instabilities that cause the wormhole to collapse. Understanding dynamic wormholes is important because any real wormhole created or manipulated by technology would necessarily go through periods of change. The averaging theorems for energy conditions are crucial constraints. While quantum effects can violate energy conditions locally and temporarily, there are theorems that constrain how much and for how long violations can occur when averaged over space or time. These averaged energy conditions are harder to violate than the pointwise ones. If they hold universally, they might rule out macroscopic traversable wormholes entirely. However, some researchers have found loopholes in these theorems, scenarios where even the averaged conditions can be violated. The jury is still out on whether nature truly forbids wormholes. Wormholes might exist in cosmological models with exotic matter. Some models of the early universe invoke exotic matter or fields to explain inflation or other phenomena. If such exotic matter was present in the early cosmos, it might have created wormholes as a side effect. These cosmological wormholes could have survived to the present day, though they would likely be microscopic and possibly stretched by the universe's expansion. Detecting such relic wormholes would require extremely sensitive instruments and clever observational strategies. The Visser-Barcelo-Liberati quantum inequalities place limits on negative energy. These mathematical inequalities, derived from quantum field theory, constrain how much negative energy can exist and for how long. They suggest that large amounts of negative energy cannot be sustained for long periods, potentially ruling out macroscopic traversable wormholes. However, the inequalities depend on assumptions about quantum field theory, a curved space-time that might not hold in all scenarios. Some researchers have argued for ways around these constraints, though the debate continues. Semi-classical gravity treats space-time classically, but matter quantum mechanically. This approximation allows physicists to study how quantum fields behave in curved space-time without needing a full theory of quantum gravity. Semi-classical calculations have been crucial for understanding Hawking radiation from black holes and for analyzing wormhole stability. However, the approximation breaks down in extreme conditions where quantum effects become very strong. Near wormhole throats or at the Planck scale, semi-classical methods might not be reliable, and we need true quantum gravity to make predictions. The concept of traversability can be defined precisely in mathematical terms. A wormhole is traversable if there exist time-like or null geodesics, paths that objects or light could follow, that pass through the entire structure from one asymptotic region to another. The throat must be large enough and stable enough for these paths to exist. If all such paths encounter singularities or event horizons, the wormhole is non-traversable. This mathematical definition makes the concept of traversability precise, allowing rigorous analysis of whether a given solution represents a traversable wormhole. Wormholes in rotating space-times face additional complications. If the space-time around a wormhole is rotating, Perhaps because the wormhole is spinning or is located in a rotating universe, the analysis becomes much more complex. The rotation can introduce frame-dragging effects, where space-time itself is pulled around the rotating mass. For a rotating wormhole, these effects would create preferred directions for travel through the throat. Some trajectories might be easier than others, and the stability properties could differ depending on the rotation rate. The achronal average null energy condition is one of the strongest constraints. This technical condition requires that when you average energy density along certain null curves, taking into account the causal structure of space-time, the result must be non-negative. If this condition holds, it severely limits or perhaps eliminates the possibility of traversable wormholes and time machines. However, there's debate about whether this condition is a fundamental law of nature, or simply a property of the matter fields we know about. Exotic matter that violates even this condition might exist in principle. Some researchers have explored wormholes in theories with higher derivative terms, in modified theories of gravity that include terms involving higher derivatives of the metric. The field equations become more complex, but also more flexible. Some of these theories allow for wormhole solutions without exotic matter, with the higher derivative terms providing the negative pressure needed to hold the throat open. However, higher derivative theories often have problems with instabilities or ghost particles, making them suspect as fundamental theories. The wormholes in these theories might be mathematical artifacts rather than physical possibilities. The question of wormhole formation mechanisms remains largely unsolved. Even if traversable wormholes are allowed by physics, how would they form? No natural process we know of seems capable of creating the exotic matter distributions needed. Some speculations involve quantum tunneling events in the early universe, or advanced technology able to manipulate vacuum energy. Without a plausible formation mechanism, wormholes remain purely theoretical constructs, solutions to equations that might never correspond to real objects in nature. Wormhole research connects to many areas of modern physics. The study of wormholes touches on general relativity, quantum field theory, thermodynamics, causality, and the nature of time. It intersects with cosmology, astrophysics, and the search for quantum gravity. This interconnectedness makes wormhole physics a rich field for theoretical exploration. Even if wormholes don't exist, the insights gained from studying them deepen our understanding of space-time and gravity. They serve as thought experiments that probe the limits of our physical theories. The weak gravity conjecture might have implications for wormholes. This conjecture from string theory suggests that in any consistent theory of quantum gravity, gravity must be the weakest force. If true, this could constrain what types of exotic matter can exist, and therefore, what types of wormholes are possible. The conjecture is still being debated and tested through various theoretical approaches. Its relationship to wormholes represents another link between different areas of theoretical physics, showing how discoveries in one domain can illuminate problems in another. Some solutions describe wormholes embedded in cosmological space-times. Rather than existing in empty space, These wormholes would be embedded in an expanding universe with dark energy or other cosmological features. The cosmological constant affects the geometry and stability of these wormholes. In de Sitter space, which has positive cosmological constant like our accelerating universe, wormholes might behave differently than in flat space-time. Understanding these cosmological wormholes could be important if wormholes exist in our actual universe, rather than just in theoretical models. The thermodynamics of wormholes raises interesting questions. Do wormholes have entropy like black holes do? Can you assign a temperature to a wormhole throat? These questions connect to deep issues in quantum gravity. Unlike black holes, wormholes don't have event horizons in the conventional sense, so Hawking's area theorem and the laws of black hole thermodynamics don't directly apply. However, some researchers have tried to develop analogous thermodynamic descriptions for wormholes, which could provide insights into how these structures would behave if they existed. Thin wormholes versus thick wormholes represent different approaches to modeling. A thin wormhole treats the exotic matter as concentrated in a thin shell at the throat, while a thick wormhole has exotic matter distributed throughout a larger region. Thin wormholes are easier to analyze mathematically, but might be less realistic physically. Thick wormholes require more careful treatment of the matter distribution, but might be more stable. Both approaches have been explored extensively in the theoretical literature, each revealing different aspects of wormhole physics. The light deflection properties of wormholes differ from those of black holes. Light passing near a wormhole would be bent by its gravitational field, but in a different pattern than light deflected by a black hole. These differences could, in principle, be used to observationally distinguish wormholes from black holes, if we ever detect them. The specific pattern of light deflection depends on the mass distribution and the shape of the wormhole throat. Some researchers have calculated what these deflection patterns would look like, preparing for the remote possibility of future detection. Wormholes could potentially be detected through their effects on background stars. If a wormhole passed between Earth and a distant star, the star's light would be gravitationally lensed in a characteristic pattern. The time delay and magnification pattern would differ from those caused by a black hole or ordinary star. Large-scale astronomical surveys that monitor millions of stars might eventually detect such an event if wormholes exist. So far, no such detections have been made, placing further constraints on the abundance of wormholes. The navigability of a wormhole depends on its internal geometry. Even if a wormhole is traversable in principle, the journey through it might be complex. The interior could curve in unexpected ways, with multiple possible paths from one mouth to the other. Some paths might be shorter or safer than others. Understanding the geodesic structure, the natural paths that free-falling objects would follow, is essential for determining how useful a wormhole would be for travel. The mathematics can be intricate, especially for asymmetric or time-dependent wormholes. Electromagnetic radiation traveling through a wormhole would experience gravitational redshift or blue shift. The redshift function determines how photon energies change as light traverses the structure. Light entering one mouth might emerge from the other with a different wavelength, shifted toward the red or blue, depending on the geometry. This could have interesting effects if the wormhole connects regions at different gravitational potentials. Communication through a wormhole might require accounting for these wavelength shifts to correctly transmit information. Some theoretical work explores whether wormholes could be used for power generation. If you could thread matter or energy through a wormhole connecting regions at different potentials, you might extract useful work from the system. However, the energy requirements to create and maintain the wormhole would almost certainly exceed any energy you could extract from it. This is related to fundamental thermodynamic limitations that prevent perpetual motion machines. Wormholes, if they existed, would not provide a source of free energy. The back reaction of matter passing through a wormhole must be considered. When objects traverse a wormhole, their gravitational fields and quantum fluctuations could affect the wormhole itself. This back reaction might cause the wormhole to become unstable or change its properties. Calculating back reaction effects requires combining general relativity with quantum field theory, a difficult problem. Some analyses suggest that the back reaction from even a single particle might be enough to destabilize certain wormholes, making them useless for transportation despite being theoretically traversable. Wormholes in anti-de Sitter space have been particularly well studied. ADS space has negative cosmological constant and different geometric properties than flat or de Sitter space. The ADS-CFT correspondence, which relates gravity in ADS space to quantum field theories on its boundary, makes ADS wormholes especially interesting for understanding quantum gravity. Much of the recent quantum computing work on wormholes uses LDS space as the setting. However, our universe appears to be de Sitter rather than anti-de Sitter, so these ADS wormholes might not directly describe real physical structures. The possibility of multi-mouth wormholes has been explored. While the standard picture involves 2 mouths, some solutions allow for 3 or more openings connected by a common throat region. These multiply connected structures would have even more complex stability and causality properties than ordinary 2-mouth wormholes. The mathematical analysis becomes significantly more difficult with additional mouths. If such structures could exist, they might allow for complex transportation networks with hubs connecting multiple destinations, though the challenges of creating and maintaining them would be correspondingly greater. Wormholes could theoretically connect regions with different physical constants. Some theories suggest that physical constants like the speed of light or the electron charge might vary across space or between different regions. If so, a wormhole might connect regions where physics works slightly differently. Traveling through such a wormhole would be especially strange, as the very laws of nature would shift during the journey. This remains highly speculative, as we have no evidence that physical constants actually vary, but it represents an interesting theoretical possibility. The problem of defining mass for a wormhole is non-trivial. Unlike a black hole, which has a well-defined mass, Assigning a mass to a wormhole system is tricky. The exotic matter required has negative energy, which seems to suggest negative mass. But the total system might have positive, negative, or zero mass, depending on how you define and measure it. This ambiguity reflects deeper issues in general relativity about how to define energy and mass in curved spacetime. Different definitions can give different answers, and there's debate about which is most physical. Wormhole solutions in various numbers of space-time dimensions have been studied. While we experience 4 dimensions, 3 of space and 1 of time, theoretical physicists explore space-times with different numbers of dimensions. Wormholes can exist in 3-dimensional, 5-dimensional, or even higher dimensional spacetimes. The properties change with dimensionality. In some cases, higher dimensions make wormholes easier to construct or more stable. Understanding wormholes across different dimensions helps physicists grasp which features are universal and which are specific to 4 dimensions. The question of whether you could see through a wormhole is subtle. In principle, light from the far side should be able to travel through the wormhole and reach your eye, allowing you to see what's on the other side. However, the gravitational lensing effects would distort the image significantly. The view might be warped, stretched, or duplicated in complex ways. Additionally, if the wormhole throat is very small, or if there's exotic matter in the way, the view might be partially or completely obscured. Visualizing what you'd actually see requires careful ray tracing calculations through the curved geometry. The paradoxes associated with wormhole time machines have been studied extensively. Beyond the grandfather paradox, there are many other logical problems that arise if backward time travel is possible. Could you create a closed causal loop where information or matter has no origin? Could you violate conservation laws by creating matter from nothing through time loops? These paradoxes have inspired many proposed resolutions, from the Novikov consistency principle to many worlds interpretations. Understanding these paradoxes helps physicists think about the nature of causality and time. Some researchers have explored wormholes as models for dark matter. Could the gravitational effects we attribute to dark matter actually be caused by a network of microscopic wormholes? This remains highly speculative and faces many challenges. The distribution of wormholes needed would have to match the observed distribution of dark matter very precisely. Additionally, wormholes would need to have the right stability properties and would have to avoid conflicting with other observations. Most physicists favor particle dark matter explanations, but wormhole dark matter represents a creative alternative worth considering. The concept of a traversable wormhole can be generalized in many ways. Beyond the standard Morris-Thorne type, there are thin shell wormholes, rotating wormholes, charged wormholes, time-dependent wormholes, and many others. Each variant has its own set of requirements, stability properties, and potential applications. Exploring this zoo of wormhole solutions helps theorists understand which features are essential for traversability and which are merely special cases. The diversity of solutions shows the richness of general relativity's mathematical structure. Wormholes might leave traces in the cosmic microwave background. If wormholes existed in the early universe, their gravitational effects could have left subtle imprints in the CMB radiation. Cosmologists have looked for such signatures, but found none. This places constraints on how many primordial wormholes could have existed and how large they could have been. As CMB measurements become more precise, these constraints tighten. The absence of wormhole signatures in the CMB doesn't prove they never existed, but it limits their possible abundance and properties in the early universe. The connection between wormholes and fundamental physics runs deep. Wormhole research has contributed to our understanding of causality, the nature of time, the relationship between quantum mechanics and gravity, and the structure of space-time at its most fundamental level. Even if no wormholes exist in nature, the theoretical framework developed to study them has applications elsewhere in physics. The techniques used to analyze wormhole stability, for instance, apply to other problems in curved space-time. The insights gained inform cosmology, black hole physics, and the ongoing quest for quantum gravity. Some physicists wonder whether microscopic wormholes could be created in particle accelerators. At very high energies, space-time itself might become unstable enough to form tiny wormholes. If extra dimensions exist at accessible energy scales, as some string theory models suggest, particle collisions might briefly create microscopic wormholes that would immediately decay. Researchers at the Large Hadron Collider have looked for signatures of such events, but found none. The negative results place constraints on theories that predict easily created microscopic wormholes. The mathematical beauty of wormhole solutions appeals to many theorists. General relativity's equations allow for these exotic structures, demonstrating the theory's richness and flexibility. The fact that you can construct traversable wormholes on paper, specify their properties precisely, and analyze their behavior shows how powerful mathematical physics has become. Whether nature realizes these mathematical possibilities remains unknown, but the mathematics itself is elegant and internally consistent. This beauty motivates continued theoretical exploration even in the absence of experimental evidence. Wormholes have inspired countless students to pursue physics. The combination of rigorous mathematics and wild speculative possibility makes wormholes perfect for capturing young imaginations. Many physicists trace their interest in general relativity and cosmology back to first learning about wormholes. In this sense, wormholes have value beyond their physical reality. They serve as gateways, pulling curious minds into the study of fundamental physics. The educational value of wormholes as tools for teaching general relativity and stimulating interest is undeniable. The relationship between wormholes and faster-than-light travel is subtle. Wormholes don't involve traveling faster than light in the usual sense. You're always moving slower than light locally as you pass through the wormhole. The shortcut nature of the wormhole lets you reach distant places in less time than light would take going the long way through normal space. But you're never violating special relativity's speed limit locally. This distinction is important for understanding how wormholes could exist without breaking fundamental physics. The future of wormhole physics might lie in quantum gravity, a complete theory unifying quantum mechanics and general relativity could settle whether wormholes can exist. Such a theory would tell us whether exotic matter is truly impossible, whether the energy conditions must always hold, and whether space-time has a structure at the smallest scales that precludes macroscopic. Wormholes, string theory, loop quantum gravity, and other approaches to quantum gravity are making progress. And their predictions about wormholes could eventually be tested as our observational capabilities improve. Wormhole research pushes physics to confront its deepest questions. What is the nature of time? Can effects precede causes? Is space-time continuous or discrete at the smallest scales? What determines the laws of physics we observe? Wormholes force us to think carefully about these fundamental issues. They sit at the intersection of everything we don't fully understand about the universe. Studying them, even purely theoretically, helps clarify what we know and what we still need to discover about reality's basic structure. The questions they raise touch on philosophy as much as physics, bridging the gap between empirical science and deeper questions about existence itself. The possibility that wormholes might never exist doesn't diminish their importance. Throughout history, physics has advanced by exploring theoretical possibilities, even ones that turn out to be unrealized in nature. The study of impossible objects often reveals why they're impossible, teaching us about the constraints that govern reality. If wormholes are forbidden, understanding why they're forbidden will deepen our grasp of space-time physics. If they're possible but extraordinarily rare or difficult to create, that too tells us something profound about the universe we inhabit. The journey toward understanding is valuable regardless of the destination. The romance of wormholes lies partly in their connection to ancient human dreams. From myths about magical doorways to other realms, to philosophical speculation about shortcuts through reality, humans have long imagined ways to transcend normal spatial limitations. Wormholes give these dreams mathematical form, translating poetic ideas into rigorous physics. Whether or not wormholes exist, they represent humanity's continuing attempt to understand and perhaps transcend the boundaries of our existence. They embody our refusal to accept limitations, our drive to explore the apparently impossible. In the equations describing wormholes, we see both our analytical precision and our imaginative reach. The mathematics of wormholes continues to fascinate theorists. Even if wormholes never exist in nature, they serve as valuable thought experiments. They help us understand what general relativity permits and forbids. They test the limits of our physical theories and reveal connections between seemingly disparate phenomena. Every new solution, every calculation of stability or required exotic matter adds to our knowledge of how space-time can be shaped and curved. This theoretical exploration has value, independent of whether wormholes are real. Wormholes remain one of physics' most captivating mysteries. They sit at the boundary between the possible and the impossible, allowed by our best theory of gravity, yet constrained by quantum mechanics and the apparent non-existence of exotic matter. They inspire science fiction authors and challenge theoretical physicists. They connect our understanding of quantum entanglement to the geometry of space-time. Whether they exist in the real universe or only in the realm of mathematics, wormholes exemplify how physics can take us beyond ordinary experience into domains where space and time themselves become fluid and malleable. And with that, we reach the end of our journey through these theoretical tunnels, connecting distant points in space and time. Wormholes remain hypothetical, existing firmly in the realm of mathematics and speculation. But they remind us that the universe may hold possibilities beyond our current imagination. The same equations that describe the moon's orbit and the bending of starlight also permit these exotic structures, bridges between distant regions of space-time. If you enjoyed these calm explorations, you can like, subscribe, or share a thought below. It helps others find their way here too, one curious mind at a time. But for now, all you need to do is rest. Let the strange beauty of theoretical physics fade into the background as your breathing slows and your thoughts quiet. The wormholes will still be there in the equations tomorrow, waiting in their mathematical realm. Good night.